Here's chapter 17, homework number 1. We start off with a flywheel of a small punch rotates at 300 RPM. And we're supposed to determine the required moment of inertia for the flywheel, and if a 25-pound-foot couple is applied, determine the number of revolutions that must occur between each punching. So we know that T is equal to 1/2 times I omega squared. Knowing that, we can solve for T1 and T2 respectively, and we know that T1 plus U is equal to T2, so we can plug in our knowns and solve for I. And we know that U is equal to the moment times the number of revolutions, which would give us 11.46 revolutions. Number 2, we have a slender rod of length L is pivoted at one end. It's released from a horizontal position and swings freely, and we're supposed to determine the angular velocity of the rod as it passes through the vertical position, and solve for W is equal to 1.8 and L is equal to 3. So now that T1 is 0 and V is going to be 1/2 omega, and I for the rod is going to be 1/12 ml squared. We can solve for T2, which should be 1/2 mv squared plus 1/2 I omega squared. And we can plug in our V and our I, and we can solve for T2 to be 1/6 ml squared omega 2 squared. And we know that U is equal to mg times L over 2. So T1 plus U is equal to T2. So we can plug in our knowns there, solve for omega 2, and get 5.67 radians per second. We also know that A is equal to R times omega squared. We know R is L over 2, and omega should be the square root of 3g over L, and since it's squared, we can just get rid of the square root, and we get A is equal to 3g over 2. And if we take the sum of the forces, we can get RA is equal to 2.5 mg, which is just 2.5 times 1.8, which is 4.5 pounds. Number 3, we have two identical slender rods that are welded together to form an L-shaped assembly, and we're supposed to determine the magnitude and angular velocity of the assembly as it passes through the position where the rod AB forms an angle of 30 degrees with the horizontal. So we'll draw a free body diagram of the situation. So we'll get V2 is equal to W times HAB plus W times HBC. Knowing that, and we know what HAB and HBC are, they come to be L over 2 sine 30 and negative L over 2 cos 30 respectively, which will give us about negative 0.183 WL for V2. And we can solve for the inertia, because they're both slender rods, we can just add them together. And we know that MAB is equal to the mass of AB is equal to the mass of BC, which we can simplify it further to get just 2/3 ml squared. And we know that T2 is 1/2 I omega squared. We can put on our knowns and get 1/3 ml squared omega squared. And so when it's at 90 degrees, we can solve for V3, which would be WHAB plus HBC, which is just V3 WL over 2. We know that T3 is equal to 0, and that T2 plus V2 is equal to T3 plus V3. So we can plug in the numbers, our knowns there, since we figured them out earlier. Solve for omega 2 and get 7.09 radians per second. Number 4, we have a wheel with a moment couple, and we're supposed to determine the resulting angular velocity of the wheel. So we know that I is equal to mk squared, and we have m and k, so we can go ahead and solve for that. The moment is just force times distance, so we can solve for that. And we know that I times omega 1 plus moment times t is equal to I times omega 2. So using that, we can solve for omega 2, which should be 3.87 radians per second. Number 5, we have a sphere of radius r and mass of m is projected along a horizontal surface, and we're supposed to do express the required magnitude of omega in terms of VO and R, and the time required for the sphere to come to rest in terms of VO and the coefficient of kinetic friction. So we can start by drawing a free body diagram of the situation, and we will get that I times omega naught minus MVO times R is equal to 0. We know that I is 2 over 5 mr squared, so we can plug that in and solve for omega, which is 5 VO over 2R. And if we sum the forces in each direction, we can get MVO is equal to mu kinetic times normal tangent times normal time, and we get that N is equal to W. We know that MVO is equal to mu times mgt. Knowing that, we can reverse that, or solve for t, use that equation to solve for t, and get t is equal to VO over mu g. 6, we have a semicircular panel attached to a circular panel. We're supposed to determine the angular velocity of the assembly after the panel has been released and comes to rest against the plate. So what we want to do first is, with the plate up, and we know the inertia of the plate is 1/2 mr squared, and the inertia of the panel when it's up is mr squared over 8. And the inertia of the whole thing is just those added up, which would come to be 5/8 mr squared. And then we know that the plate doesn't change in either state, so the inertia in state 1 and state 2 is the same. But the panel in state 2 goes to mr squared over 4. And the state 2 inertia is just both those summed up, which is 3/4 mr squared. And we know that I2, omega 2, I1, omega 1 are equal to each other. We can just plug in and solve for omega 2, which is 5/6 of omega 1. Number 7, we have a bullet that is fired horizontally at a velocity VO and a height of 1/2 R into a wooden disc of a much larger mass. And we're supposed to determine the linear velocity and the angular velocity of the disc immediately after the bullet has penetrated the disc, and determine the ensuing motion of the disc and its linear velocity after the motion has become uniform. So first what we'll do is draw a free body diagram of the situation. We can sum the forces in either direction, get N is equal to W, and for T is equal to 0, we would get V1 is equal to MV naught over big M. And if we sum the moment of the center of gravity, sum of the forces equal to sum of the effective forces. And we know that I is 1/2 mr squared. We can plug that in. And we know that H is 1/2 of R. So after we do all that, we can solve for omega, which should be mv naught over large M times r. And then for the uniform motion part, we know that mvo times h, or 1/2 r is equal to m r omega times r plus 1/2 mr squared times omega. Simplifying that down, we have 1/2 mv naught r is equal to 3/2 mr squared omega. And solving for omega there, we get mvo over 3mr. And since v2 is equal to r times omega, we can get rid of the r, and v2 is equal to mv naught 3m. Number 8, we have a plank of mass 15 kilograms that's resting on a pivot point, and a gymnast is standing on another side of the plank while another gymnast jumps at a height of 2.5 meters and strikes the plank, and we're supposed to determine the height to which the gymnast will rise. Gymnast A will rise. So if we take the moment about the pivot point, we can get MBV1 times L is equal to ID omega 2 plus MAV2L plus MBV2L. We know that ID is 1/12 M times 2L squared. So we can plug that in. If we plug that in, we can solve for W and get solve for omega. Omega, we would get 3MBV1, and then the mass of the plank, the mass of person A, mass of person B times L. And then we know that V1 is equal to the square root of 2GH. Knowing that, we can solve for V1. We know that V2 is L times omega. Combining all of those together, we should be able to solve for V2, which is 3.76 meters per second. And using that, we can plug that into V2 is equal to square root of 2GH2, and solve for the height that the gymnast should reach, which should be about 0.72 meters.